All right, welcome back, folks. In this video, we're going to take a look at a set of existence theorems. Now, at the time of this recording, I'm not sure what chapter this lesson is going to up in when it's all said and done. So we'll just call it question mark point 1 for now. Okay, content will stay the same. Objective is going to be to apply three existence theorems: the intermediate value theorem, the extreme value theorem, and the mean value theorem. Okay, these all come together because they're all theorems that guarantee the existence of a value on a function given a certain set of criteria. So let's start taking a look at those. First one we're going to look at is the intermediate value theorem. Now, this is something we already talked about way back in chapter 1. I do want to present these all together just to show you the similarities and differences between them. Intermediate value theorem stated that if f is a continuous function interval a to b, so I've got some function f of x here, and it is continuous. Okay, I can draw it without lifting my pencil, and it's continuous from a to b here along those x values in particular. Then for any value L between f of a and f of b, there exists at least one number c in a to b such that f of c equals L. Okay, so in other words, that means that I can pick any value on this y-axis between f of a and f of b, and I'm going to have at least, so for example, we pick here, I'm going to have at least one c value between a and b that gives me that y value out. Okay, at least one. As you can see, there's some spots where there'd be several. Okay, but I'm guaranteed at least one by that intermediate value theorem. Now, the key for the intermediate value theorem working is that my function must be continuous on that interval. If it wasn't, I wouldn't be guaranteed to have that c value that gives me the L I'm looking for. So for example, here I've got a partially filled in function. Let's say that we have some arbitrary L value right here. Okay, well, it'd be pretty easy to kind of connect my dots here to finish this function off. And make my function so that it is defined for all values of x. Okay, but by not being continuous, by having a jump discontinuity, I'm missing this L value here. There's no x's between a and b that give me that L out. Okay, so again, before I can apply the intermediate value theorem, I need to know my function is continuous over a and b. All right, so let's go ahead and look at applying the intermediate value theorem, problem 1. Part A says, let f be the function defined by f of x equals this polynomial. We want to know, can the intermediate value theorem be applied to guarantee a value of x in the interval 1 to 5 such that f of x equals 1? Okay, so in other words, we want to figure out, do we have a solution to f of x, this polynomial, equals 1 on this interval 1 to 5? Now, we could obviously solve the equation, see if we have that solution, but otherwise we can use our intermediate value theorem to determine whether or not it will happen. So let's go ahead and do that. What I'm going to do for that is I'm going to look at my endpoints plugged into my function. So we'll look at f of 1, which will be equal to 2 times 1 squared minus 4 times 1 minus 5. So we have 2 minus 4 is negative 2 minus 5 would be a negative 7. And we'll also look at f of 5, the other endpoint. All right, that's going to be a 2 times 5 squared minus 4 times 5 minus 5. Okay, so 25, 50 minus 20 would be a 30 minus 5 would be a 25. Okay, and that value of 1 fits within this interval of output values of my y values, and also my function is continuous. Now, it doesn't state it explicitly up here that we have a continuous function, but we do know that polynomials are continuous. Okay, so I'm going to say yes, I can use my intermediate value theorem. And for justifying my answer, what I'd do is I'd say since f of x is continuous, on 1 to 5. And again, how do we know that? We know it's a polynomial. All right, and that value we're looking for, 1, fits within this range, and f of 1 is less than the 1 we're looking for, which is less than f of 5. Okay, by the intermediate value theorem, I feel like I could have capitalized that because it's a name, but oh well. There exists an x on our interval 1 to 5 such that f of x is equal to 1. All right, so there's how you justify the existence of that x value, okay, on that interval using the intermediate value theorem. All right, let's take a look at an example that actually doesn't have a solution. And again, we'll justify that using the intermediate value theorem. So this time we have our g of x is a polynomial once again. And we want to know, can we find an x value on the interval 1 to 5 once again, such that g of x equals 0? Okay, so can we find a 0 of this polynomial on this interval? Again, what we'll look at is we'll look at our endpoints plugged into our function. So we'll look at g of 1 once again, which will be 3 times 1 squared minus a 2 times 1 squared. Whoops, so we mean to the third power. Same answer though. Plus a 1 plus a 3. Okay, that's going to give me a 5. And the same thing for g of 5. This number ended up a little bigger than I meant to have, but oh well. 3 times 5 to the third minus 2 times 5 squared plus 1 plus 3, and we meant plus 5 here, didn't we? Okay, when I plug that in, the calculator says that's equal to 333. Okay, so now again our function is continuous, so we can apply the intermediate value theorem. All right, but notice the 0 doesn't fall within this range of 5 to 333. Okay, so this is going to be inconclusive. It may have a 0 on this range, it may not, but what we have here for information doesn't tell us that. Okay, so here, can I conclude it? We'd say no, and for my justification, well, the 0 we're looking for is less than g of 1, which is less than g of 5. Okay, so that's how we know that's not going to work. All right, next one we're going to look at is the extreme value theorem. Again, this is something we've already dealt with. What we want to do with this lesson is put all of the existence theorems together to kind of compare and contrast them. This one says that if f is continuous over the interval a to b, okay, so once again we have a function that's continuous along some x values, a to b, then there exists an absolute maximum value for f and an absolute minimum value for f on the interval ab. Okay, so if we're continuous on that interval, we will have both an absolute maximum and an absolute minimum, a highest and a lowest point. Okay, we also know that the absolute minimum maximum will occur either at the critical points of f, okay, or the endpoints of the interval. There's the type I was looking for, or. Okay, so in this case we see that we have an absolute minimum at a critical value, one of its turning points, and then the maximum is at the endpoint. We could have the opposite of that. Okay, we could have both at critical points, both at endpoints. There's different combinations depending on the function. Now, once again, continuity is the key for being able to apply my extreme value theorem as well, just like with the intermediate value theorem. Because if I had a function, let's fill in this f of x and make it not continuous. So for example, let's throw a vertical asymptote in there, I could easily come up with a function that doesn't have an absolute maximum, okay, or absolute minimum, okay, with that interval because our function isn't continuous. Okay, or we can kind of flip that around. We could make it so that maybe it does have a minimum. We can make this guy turn around like that, so our minimum would be here, but there'd be no maximum. Or we kind of do the other way around. Okay, either way with the extreme value theorem, key thing we want to point out here is continuity is the key for being able to apply that theorem. All right, last one for you then, the mean value theorem. This will be the big new one for the day. If f is a continuous over ab and differentiable over the open interval ab. Okay, so again, we have a function that is continuous but then also differentiable from a to b. Then there exists at least one number c on that open interval ab such that the derivative of c, f prime of c, is equal to the function's average rate of change over AB. So in other words, as long as my function is both continuous and differentiable, if I find my average rate of change of that function over that interval, okay, just kind of the slope of the secant between these 2 points, I'll be able to find at least one value c whose tangent line has the same slope. Okay, these 2 lines would be parallel here. Or in other words, f prime of c is equal to my difference quotient, okay, the slope between those 2 points. Now with the mean value theorem, the key to making things work is that it's both continuous and differentiable. Okay, continuous because if we have different holes in the graph, I think it'd be easy to see, just like with our other 2 theorems, we could make functions that don't follow what we're looking at, okay, don't follow what we're looking for. Here's the differentiable piece. If I have a function set up like this, my average rate of change would just be a 0. Okay, the slope of my secant line would be 0. And if I don't have to draw a function that's differentiable, it'd be pretty easy to come up with something that never has that slope. Okay, I could make something with some sharp corners like this with some cusps. Okay, so I just connected the dots here so that f of x is continuous. I can draw it without lifting my pencil, but since it has that sharp corner, that sharp cusp, all right, it's not going to be differentiable. Okay, what I need to get this 0 for the tangent line, for the slope of the tangent line there, is I need a continuous and differentiable function. I need something that's smooth, which is going to have those nice horizontal tangents with the slope of 0 as well. Okay, so the big difference with that mean value theorem today is our function needs to be both continuous and differentiable. All right, so let's take a look at applying our mean value theorem. Problem 2 part A says let f of x equal this radical function. Okay, and find the value c that satisfies the mean value theorem for f on the interval 1 to 3. Okay, so in other words, we want to find the x value between 1 and 3 that has the same slope of the tangent line as my average rate of change here. Okay, so let's go ahead and do that. I'm going to break this problem down into 3 parts. Just going to do part 1, part 2, part 3 here. Part 1 is going to be find the average rate of change. So in other words, we want to find f of 3 minus f of 1 divided by 3 minus 1. Okay, so the slope between the points on this function from 1 to 3 here. All right, so let's plug those in. So it'll be the square root of 4 times 3 minus 1 minus the square root of 4 times 1 minus 1. Whoops, and that's not a 1 there, is it? That's a 3. Wake up. divided by 3 minus 1, which is a 2. Okay, so in other words, 4 times 3 is 12, minus 3 would be a 9, square root of 9 is a 3, minus 4 times 1 is a 4, minus 3 would be a 1, square root of 1 is just a 1. Okay, so we have a 2 over 2. In other words, just the 1. All right, so what we're looking for here then is the point on this interval 1 to 3 that has a slope of 1, okay, the same as this average rate of change. So for that, what we're going to have to do is find the derivative. Okay, so find the derivative of this function. Now for that, let's rewrite our f. Instead of using roots, let's say that f of x is equal to, we'll say parenthesis 4x minus 3 to the 1/2 power. Okay, let's rewrite in a form that's a little more easy to take the derivative of. Okay, finding my derivative then, f prime of x, we can use our power rule. We'll multiply by the power, the 1/2, times the 4x minus 3 to the power minus 1. 1/2 minus 1 will be a negative 1/2. All right, then since this is a composite function, we have an outer function of raising the 1/2 power and the inner function of the 4x minus 3. We do need to use our chain rule and multiply by the derivative of the inner function. Now in this case, that's just going to be a 4. All right, so we can clean this up and rewrite it as the fraction. We've got 2 on bottom, 4 on top. They'll turn into just the 2 on top. Okay, over, we can put the 1/2 power on the bottom. I'm just going to rewrite that as a root here. All right, so there's my derivative. Okay, if you give me an x value, we can figure out the slope of that function, the instantaneous rate of change, okay, at that value. Last step then, we want to figure out where our derivative is equal to 1. So we can say solve the equation. I want to know where f prime of x is equal to 1. Okay, so in other words, where this 2 over square root x, 4x minus 3 equals 1. And for this step, you're just going to solve whatever type of equation you end up with. Okay, here we have a rational equation with a radical in it. Anytime there's fractions, probably a good idea to clear the fraction out. I'm going to multiply both sides by this root 4x minus 3 to cancel my fraction out. That's going to leave me with just the 2 on the left is equal to 1 times that root 4x minus 3. And then from there, we can just square both sides to get rid of the root. And then we're back to algebra 1. Get the x by itself. And we end up with, when x is 7/4, we'll have a slope, an instantaneous rate of change of 1, okay, which matches this average rate of change. All right, we'll say that's the big question for this lesson, okay, applying that mean value theorem. Part B is the same idea, a little bit simpler function to work with though. Why don't you take a minute, pause the video, work through part B, and then you go ahead and press play to check your answer. All right, and the last thing we'll do with this lesson is kind of take a look at all of our theorems, all of our existence theorems kind of within the context of the same problem. Okay, this will be all about kind of deciding which theorem we're looking to apply for a given question. So problem 3 says selected values of a differentiable function f are given in the table below. We want to determine whether each of the following statements must be true. Okay, so not necessarily that they're true or false, but whether they have to be true or not. Okay, so we've got some x values, we've got our f of x values. First question asks, there exists a value c on the interval 2 to 5 such that f of c equals 10. Okay, so first thing I want to ask myself is, which theorem is this one asking about? Well, when we want to know if there exists a value of the f of x, the original function, that's going to be the IVT, the intermediate value theorem. And to apply that, what we need is continuity. Now, here we're given that our function is differentiable. Now, it's differentiable, it means it is continuous. Remember, that doesn't work the other way around, but if it is differentiable, it's continuous. If it's continuous, it's not necessarily differentiable. So then what I'll look at is I want to ask myself, does 10 going to fit in between f of 2 and f of 5? Well, f of 2 is a 1, f of 5 is a 31, so yes, 10 fits within that range. So that's why I can say yes for this one. And my reasoning would be that f of 2 is less than 10, which is less than f of 5. Because that's why I'm able to apply my intermediate value theorem. All right, part B asks, there does not exist a value c on the interval 2 to 5 such that f of c is greater than 31. So in other words, is 31 our absolute maximum for this function? For that, we're dealing with the extreme value theorem. And it looks like, yes, 31 is the highest value we see on this table. Okay, but we know by the extreme value theorem that the absolute mins and maxes will either occur at my endpoints, okay, or any critical values in between them. Now, we don't know anything about the derivatives between 2 and 5, so there may be other critical values, there might not be. Trick with this one is we'll say, no, we're not sure if this statement has to be true. Okay, it's not necessarily false, but we're not sure if there's anything above 31 here, because again, we don't have all the information for the points in between. Okay, so I can't make a conclusion using my extreme value theorem. All right, last one here, there exists a value c on the interval 2, 5 such that f prime of c equals 10. All right, so if we're looking for the existence of a value for our derivative, that's going to be the mean value theorem. And for that, we want to figure out, do we have a c value that gives us a slope of 10 on this interval? Well, for that, what we can do is we can check our average rate of change at our endpoints. So we can look at f of 5 minus f of 2 divided by 5 minus 2, which will be a 31 minus 1 over 3. So in other words, 30 over 3, which is equal to a 10. All right, so that is my average rate of change. My function is differentiable, meaning that by the mean value theorem, we can say yes. Okay, there has to exist a c between here that has that same instantaneous rate of change as the average rate of change.